In this section, we're going to start with a comparison between UAS and UAV, defining these terms in the world of aerospace technology. Next, we'll explore the balance between accuracy and resolution, understanding how these factors play a crucial role in UAS mapping. We'll also delve into the different types of accuracy and land surveys, uncovering the various methods and techniques used in this field. Photogrammetry, a key technology, will be discussed to give you insights into how it works and its significance. Then, we'll tackle the age-old debate of fixed-wing versus multi-rotor versus VTOL UAVs, dissecting their strengths and applications. And, of course, we can't forget about payloads, where we'll explore the equipment and tools that drones can carry for various missions. So, let's embark on this journey of exploration together as we dive into these topics. We will start by clearing up a common confusion, the distinction between an unmanned aerial vehicle, UAV, UV, and a drone. Spoiler alert, they're the same. However, the term UV can be used for any unmanned vehicle, including aerial ones. On the other hand, UAS is composed of at least three key components: the UAV, a ground-based controller, and a communication system that links them together. These UAVs come in various sizes, but they all fall within a weight range of 0.5 to 55 pounds. One of the most important aspects is that UAS operations are being unmanned or pilotless, a feature that has a history dating back to 1917. And finally, let's answer the burning question: why are drones such a big deal right now? As we noticed, in recent years, the drone industry has experienced a remarkable transformation. At the heart of this evolution lies a crucial reason, which is the invention of lithium batteries. These lightweight, high-energy density power sources have revolutionized the drone landscape, raising it from a hobby to a dynamic, multi-billion-dollar industry, with applications ranging from aerial photography and surveying to agricultural and disaster response. Accuracy and resolution are two fundamental concepts in the field of remote sensing, cartography, and surveying. They both play a significant role in determining the quality and usefulness of spatial data. Here's how they differ. Accuracy refers to how close measurements or data values are to their true or real-world values. It indicates the degree of correctness in the data. In other words, accuracy assesses how well the data represents the actual attributes of the object or phenomenon being measured. High accuracy is crucial when dealing with applications where precise measurements are essential, such as in surveying, navigation, and scientific research. A good example of this is GPS accuracy, which measures how closely GPS data matches on the actual positions of the Earth's surface. Resolution, on the other hand, refers to the level of detail or the smallest distinguishable features that can be captured or represented in a data set. It's the ability of a sensor or instrument to differentiate between adjacent or closely spaced objects. Resolution is often categorized into spatial resolution, spectral resolution, temporal resolution, and radiometric resolution, depending on the type of data being considered. For instance, ground sampling distance, or GSD, is an example of spatial resolution. It represents the physical size of each pixel in an image and is a key factor in determining the level of detail that can be observed in an aerial or satellite image. In summary, accuracy deals with how closely data values match the true values, while resolution pertains to the level of detail and ability to distinguish features in a data set. Both accuracy and resolution are critical considerations when selecting and analyzing spatial data for various applications. Let's dive into the fascinating world of GPS accuracy. We can categorize it into two main groups: high accuracy, encompassing techniques like RTK and PPK, and medium accuracy, where we find the standalone method. RTK, or real-time kinematic, and PPK, or post-processing kinematic, are the stars of the show when it comes to enhancing GNSS accuracy. These techniques are particularly valuable in fields like surveying, mapping, and georeferencing in UAS operations. On average, RTK and PPK can achieve accuracy levels of up to 1 centimeter, making them exceptionally precise. Now, let's define those highly accurate corrections. First, post-processing kinematic is a correction technique where the data collected is recorded by the receiver and processed after the survey mission is completed. This method typically achieves an average accuracy of up to 1 centimeter. Second, real-time kinematic is a correction technique that provides real-time, high-accuracy positioning by transmitting real-time correction data from a base station to the rover. On average, RTK can achieve accuracy levels of up to 1 centimeter in real time, allowing for precision applications that require immediate and precise positioning. Now, let's talk about standalone accuracy, also known as single-point positioning. This is the level of accuracy achieved without relying on any external corrections. It's a standalone champion. Single-point positioning typically achieves an average accuracy of around 5 meters, which may be sufficient for certain applications where high precision is not the primary requirement. And speaking of navigation systems, you've probably heard of GPS, right? Well, it stands for the Global Positioning System and is primarily associated with the United States. GPS is a subset of GNSS, the Global Navigation Satellite System, which is a broader term encompassing multiple satellite systems worldwide. While GPS is specific to the United States, GNSS includes systems like GLONASS from Russia, Galileo from Europe, and BeiDou from China, and more. It's quite the team working together to help us navigate our world with precision. Land surveying is a remarkable field that involves measuring and mapping the Earth's surface and its various features. Why? Well, it's all about establishing property boundaries, crafting precise maps, and providing critical support for construction and development ventures. In the world of land surveying, we often encounter different accuracy standards. These standards are crucial to ensuring that the surveys meet the specific requirements of various projects. For instance, there's ALTA, with a required horizontal accuracy of just 2 centimeters. This meticulous level of accuracy is particularly important for projects involving commercial real estate transactions, where precise property boundaries are of utmost importance. When it comes to topographic surveys, we're looking at a vertical accuracy of up to 6 centimeters. This level of precision is essential for mapping out the contours and elevations of a landscape, which is invaluable information for architects, engineers, and urban planners involved in construction and development projects. Now, in some cases like zip maps, we might have a bit more flexibility with horizontal accuracy of about 1 meter. This standard may be suitable for projects where a higher level of detail is not as critical, but a general overview of the area is still needed. Each of these standards serves a unique purpose in the world of land surveying, ensuring that we can meet the specific needs of various projects. Whether it's for large-scale commercial developments or smaller-scale endeavors, having a range of accuracy standards allows land surveyors to tailor their approach to the demands of each individual project. This adaptability is a testament to the versatility and importance of the field of land surveying in modern construction and development. Photogrammetry, a remarkable technique, utilizes the power of photographs to measure and map the physical features of objects and landscapes with precision. It involves the analysis of image geometry and positioning, leading to the creation of highly accurate measurements, detailed models, and comprehensive maps of real-world objects and scenes. Imagine it as crafting a visual representation of our environment through the art of photography. Now, let's introduce the stereoscope and its world in the art of photogrammetry and UAS mapping. The stereoscope is a remarkable device that allows us to view two separate images, often photographs, in a way that magically transforms them into a three-dimensional perception. It achieves this by presenting slightly different perspectives to each of our eyes, just like our natural binocular vision. This breakthrough in 3D visualization revolutionized the practices of mapping and 3D modeling professionals. It significantly enhances their comprehension of topography, landscapes, and structures, allowing them to extract even more valuable insights from the imagery they capture. Moreover, it paved the way for various computer vision technologies such as virtual reality and game designing. Interestingly, the very first practical stereoscope, known as the Wheatstone stereoscope, emerged in 1838 thanks to Sir Charles Wheatstone. This invention laid the foundation for the widespread use of stereoscopic viewing devices, ultimately contributing to the spread of 3D modeling and computer vision during the 19th and 20th centuries. Finally, let's define remote sensing. Remote sensing is a technology that involves acquiring information about an object or phenomenon from a distance, typically from aircraft or satellites, using sensors and instruments. So, the next time you explore a photogrammetric map or work on a UAS mapping project, remember the remarkable connection between photogrammetry, stereoscopes, remote sensing, and the precise mapping of our world. Let's explore the captivating realm of UAS mapping payloads, each with its distinctive capabilities that empower various mapping applications. First, we have RGB, or red, green, and blue, cameras, which function much like our human eyes, capturing visible light imagery. These cameras provide vibrant, detail-rich images and find utility across diverse fields, including aerial photography, visual inspections, and the creation of orthomosaic maps. RGB cameras are known for their adaptability, cost-effectiveness, and the ability to produce high-resolution images suitable for visual interpretation. However, they are limited in that they cannot capture data beyond the visible spectrum, which restricts their use in tasks like vegetation analysis or environmental monitoring. Next, we have LiDAR, or light detection and ranging payloads. LiDAR systems emit laser pulses and measure the time it takes for these pulses to bounce back from objects on the ground, creating highly detailed 3D point clouds. LiDAR excels in terrain modeling, infrastructure inspection, vegetation analysis, and the generation of precise elevation data. It provides highly accurate and dense 3D point cloud data, making it ideal for mapping complex environments and capturing fine details. However, it's important to note that LiDAR systems often come with a higher price tag, and processing LiDAR data can be resource-intensive. Finally, there are multispectral sensors, which capture light in various spectral bands beyond the human vision range, including infrared and ultraviolet, thus revealing object reflectance properties. These sensors shine in tasks such as assessing vegetation health, monitoring crops, and conducting environmental studies. Multispectral sensors offer insights beyond what RGB cameras can provide by detecting specific wavelengths associated with materials and conditions. However, they may have a lower spatial resolution than RGB cameras, and analyzing their data often requires specialized knowledge. In the world of UAS mapping, selecting the right payload hinges on your specific mapping objectives, budget constrictions, and data type requirements. Frequently, a combination of these payloads is employed to capture a comprehensive dataset, opening up new horizons in geospatial intelligence. The possibilities in this field are truly limitless. Here are some other unusual payloads.